Sorry for the guys. Right, let's get started. So for this time, we were supposed to read section 3.1 and 3.2. And it's actually interesting because it's about a topic that's not usually covered in first course functional analysis. Actually, it's the functional derivative. So what does it mean to take the derivative of a map from one vector space x to y? And it's as we'll see, it's quite counterintuitive at first, but it's actually a nice generalization of what it means to take the derivative of a map, and actually it turns out to be stuff for even for machine learning. When you take the derivative of a map that takes maybe a matrix and matrix, in that case, it's this notion of the section that we had to read for today about the definition of the derivative of map f from x to y. Generic norm space. They don't specify if it's Banach or Hilbert. And then the first application for that is for actually optimize. There are multiple cases of theory or Euler-Lagrange equation where you specify a problem as an optimization problem over a function space. Optimization in infinite dimension. Then you can try and use the classical optimization criterion to find sort of that. Start with the functional derivative. Have a map f x to y, both of them being just normal spaces. And we say that f is differentiable. In the book, they just say differentiable. This concept is widely known as Cauchy derivative. There are multiple complex of functional derivatives. Cauchy is sort of the strongest one. They're differentiable at some point x0 in x if we can find some bounded linear operator from x to y such that basically it converges to f of x minus f of x0 L of x minus x0 as the between x0 0. It sort of looks like the derivative that we saw calculus, slightly different. And we might be curious, okay, why do we have to take a continuous linear operator? And spoiler is that one of the reasons for that is that we keep the derivative as a linear approximation. So, for example, when you take the Taylor approximation of a function, the first derivative appears as a linear approximation of your function. This definition, that's what it's trying to capture. You go to look at some other definitions like the Gaussian derivative, basically weaker than that in that it says, okay, the directional derivative always exists, but it's not necessarily a linear map or even depending on the thing on what your problem is, you have to do a weaker one. But yeah, let's talk about the type signature that derivatives. The derivative of a function from x to y, it's a function from x, a linear operator x to y. It's a bit weird because you have x, which is a function from x to y, and the derivative is a function from x to a function from x to y, which seems weird when we get the classical derivative, which, oh, it's just a function r to r. But actually, if we look at the derivative classically, it's in for the context. For example, oh, let's take the derivative of a function from Rn to r, that gradient, and it's a function from Rn to Rn. Because you take an x at input, turns a vector output, have a function from Rn to Rm, and the derivative of that would be the Jacobian, and that's a function from Rn to a matrix Rmn. Already, this third row, it's slightly more clear that we get something that looks like linear operator because there's a matrix from Rn to Rm. That's when you look at that, it starts to make more sense why we define derivative as something that takes an x and have a linear map from x to y. It also makes it clearer that actually when we took derivative on top, it should be actually the primal there. But of course, r being just a scalar field, it's its own primal. Really, when you take a map from x to r, the derivative is max map from x to dual of x. Interesting then that actually we're just confused about the classical derivative. It really makes sense to say, oh, is it just a map from a linear map? In the other case, it's the two.
Right. I have a questions.
Yeah, go on.
What's the dual? Can you remind me the dual thing?
So the dual, so if you have a vector space, say x, the dual space is the space of all linear forms. So if you take a function from your vector space to the reals, and you want that function to be linear, any linear function from Rn to R, that would be something called a linear form, and if you can take it's actually formed a vector space. From a vector space X, you get a vector space of linear forms on it, and usually you can find some good results about this. So, space in finite dimension, for example, the space of a finite dimensional vector space is isomorphic to it.
Uh,
It's
Another
also
way, if you want a geometric way to see it,
yes,
at least in like infinite dimension, is that if the primal is like the set of points, so for example, like in Rn, you just pick a point and that's your value. The dual space is the set of hyperplanes in this space. And
Right.
it's dual because you can essentially go back and forth from a point to a hyperplane defined by it, using essentially the vector, the scalar vector operation.
also if you think of a vector is just a column of numbers, then an element of the dual is just the row vector. So when you take the transpose, that's a vector transpose is actually not a vector, it's a covector or an element of the. It's,
Oh.
it's one of the slightly confusing things that actually it looks exactly like a vector because it's also characterized by n numbers, but actually it's not a vector, it's an element from a different space.
The problem is when you have infinite dimensions, because then the things get more complicated as the dual can be larger than the primal space.
Yeah,
So
exactly.
they are not necessarily isomorphic.
It also makes I've discussed that higher derivatives like as the derivative of the derivative of that it's even more complicated, right? So usually we don't get much further than the first derivative.
Right. Thanks. Let me look into it. I'll remember to look into it after this.
Can do it, but it's pretty gnarly. So key results of that section for scalar functions, Cauchy derivative is just the same as the classical one, so yay. Uh, Pretty useful for them that okay, the derivative is when it exists, it's unique. Thank God for that. And yeah, the nice thing about the derivative is that okay, when f is differentiable, the chain rule still works. The composition function, you can just apply the formula with some care as to okay, what are the types of arguments, which space am I working in. But generally, chain rule still works, even though so the exercise just show okay, chain rule works for functions from x to r, but in general it still. Now to the next section, that was more about optimizations. Remember about graduate real analysis course. Uh, Reasonably easy to show that if you have a function from R to R that is dimensionable, and x star is a minimizer of f, then derivative f at x star is equal to 0. That necessary condition, but efficient. And the efficient condition, you have some point where derivative is 0 and the second derivative is positive, then you have a minimum of f. However, that yeah, maybe taking the second derivative in general case might be gnarly. Don't have don't want to take the second derivative. Another way to show is you can just take f convex, so there's a solution of convexity for functions, convex function and stationary point, and you have a minimum. In the book and these kinds of problems, generally refer to this characterized. Part now is extra, so gâteau derivative. I wanted to mention it because gâteau in French means cake. It's always very funny to me. But yeah, so the gâteau derivative is more maybe one of the first things you might try if you want to generalize the derivative. Basically the directional derivative. Fine at x0, but then you also have to give it a direction h, and then you just take tau, which is just a scalar, so then this expression here is a function of tau, is just a function from r to r, so it works. R to x, sorry, r to y. So basically you doing this, just the good old derivative, and so the gâteau derivative defined as a function from x to x, yeah, point where you start and the direction, and sort of difference between the definition and gâteau derivative. Not necessarily linear and not necessarily actually, even if it is linear and continuous, does not mean that the function is Cauchy differential. Yeah, here we dragons. Sometimes you have to do that. Yeah, I did want to give some examples of the optimization problems. So one example is in optimal control. So control theory, you generally have something like, say, a robot where you have motors that you drive the wheels of your robot, but then your robot is subject to some constraints, right? It subject to gravity, maybe some wind, maybe the floor is slippery. So even if you don't do anything, but we have some constraint, at least it will have some movement just in the constraints of physics. And what you have control as the operator is the u, which is the control term. And generally you want to find, okay, some u that achieves some goal. So maybe I want to move my robot from point A to point B, but you also have some constraints. So generally you express this as a functional that you try to minimize. So j here is functional. X means trajectory, initial and ending times. They're actually, so they're called endpoint conditions, or typically a loss starting an endpoint. Then you have the integral of some function over your trajectory, which is the cost. Like maybe you want to minimize how much energy you're taking robot or something like that. These translate to our equation because you have differential equations, then some inequality, then equations. But actually, do can at least sometimes be embedded into the top. So the simplified optimal control still has a optimization problem, and you can still try to use luck on the general case. Yeah, the other example I wanted to give was actually if you head to the next section, the exercise reward. Let's say I have points xy in Rn, and I start by defining just the segment between x and y, and I want a curve length functional of a functional that takes function, so a differentiable function from 0 to 1 Rn, and 0 here means that basically I'm perturbing this straight line, and the idea is that any point, any curve from point x to y can be expressed as my straight line plus some perturbation. The reason I'm taking this perturbation is that just taking the space of curves from x to y is not a vector space. These perturbations, because they at the endpoints they have to be 0, then it's a vector space that you can reason about. The problem is, okay, find the minimizer of curve length functional, i.e. what's the shortest path x to y. I've been trying to solve it using chapter. It's a bit quite finished it. Next section, the exercises are mostly okay. The Lagrange equations prove that the shortest path between x and y is indeed a straight line. That in other geometry. Yeah, that was the recap for today. Does anyone have any questions about the slides or about maybe exercise or quite?
Yeah. In the last slide, what is gamma?
Yeah. So gamma here. So gamma is a curve. Let's say lambda here is okay. The linear interpolation between x and y. And then I want to say, okay, what is the shortest curve between points x and y? So a curve being just a function from 0 to 1 that starts at x and ends at y. But instead of directly working on functions, I'm saying, okay, any curve from x to y is just the straight line plus some perturbation. The reason is that then if I were to talk about the perturbations form a vector space, which I need to have the derivative. Think of gamma gamma here as just some perturbation around your
Right.
your straight line.
What is lambda prime? Is lambda prime
It's the derivative. I've
Oh.
taken the dash for the derivative. I should have taken the dot, but derivative. Because the length of a curve is just integral of the norm of the derivative at that.
Oh, right. Wait, I thought because in the book they use the square root of 1 plus the
Yeah,
derivative.
that's
of
for
that.
for a curve, like a graph. If you take some function from R to R and you want to say, okay, what's the length of the graph as I draw it, then you have the one which actually comes from the fact that your curve is parameterized by the point t f of t. So when you take the
Right.
derivative of that, the t becomes 1. So that's why you have 1 in the exercise.
Right. Got it. So in this case, that's like more like a gradient, the lambda prime, and the gamma prime.
Yeah, exactly.
Okay. Thanks.
That's why you have the norm, because it's a vector in.
Sorry, I
Questions?
was away for like 5 minutes or less. What did you cover in this little span?
Where did you leave?
Uh, After this, okay, go on. Okay, yeah, the convexity part I heard of. I think anything after the
Okay, so
convexity.
you just
Okay,
missed
these
the
two.
extra part about the two derivative.
Mm-hmm.
An example about optimal control. I mean, I didn't take took the general for gnarly. Then another example about, okay, what's the shortest curve between 2 points?
Okay. And for the shortest curve, you said essentially you treat it as a line and a perturbation.
Yeah.
Because it's easier to handle, or
So the reason that if you take just the curves, the functions from x to y, they don't form a vector space. You don't have a zero map. The reason I do this, okay, say I take my straight line and just a perturbation around it, and then the
it's
zero.
like changing to like from affine to linear.
Yeah,
Essentially.
exactly.
Okay.
So let's try. Right, go on.
Right. the Gateau derivative, is it in the book or is that extra?
So the book does not talk about the Gateau derivative. They just talk about the Frechet derivative. Because if you want to go into functional derivatives, it's a bit of a complicated because
Right.
like
So the directional derivative is basically you give it a functional and you give it another functional that's the direction, and then you get the change, right?
If you want an idea in terms of neural networks, do you know what they are, backpropagation, that type of things?
Right.
Okay, in any case, you can see the Frechet derivative. You can see it as a backpropagation, giving you the entire gradient, while the Gateau derivative is more like forward differentiation, giving you like a scalar product with the gradient and the direction you care about. So like in implementation wise for neural networks, the gradient using backpropagation with respect to the loss is the Frechet derivative in terms of the function space of neural networks.
Right.
thing is that in finite dimension, it's easy to handle. As soon as you step into infinite dimensions, it gets a lot more complicated. So you can have the problem of the space not being perfect, and maybe sometimes, sorry, my derivative does not exist everywhere, so I have to restrict on a small space. Yeah, well, whenever people try to use derivatives in actual functional analysis, sometimes you have to jump quite a lot of hoops. In finite dimension, it's at least. A good example of that, earlier in the math channel, someone put a paper about general matrix functions. You have maybe a function that takes a matrix and returns a matrix. Take the derivative of that. What the paper did was they actually used the Frechet derivative to get their result. That they derived an algorithm for backdrop over matrix. Yeah, don't look at the many documents I have. Did anyone try to do any exercises part? Did anyone get stuck? Hearing see many people. Good. I think, yeah, I mentioned some exercises. So yeah, there was a few small easy ones and a few crunchier ones. Thing is that a lot of these exercises were about complexity, kind of exercise you might see in a introduction to optimization or that. So I'm not sure if we those or if we want to pick on the go for the derivative ones. I have to take. Yeah, I mean, I'm waiting for comments here on if you guys want to as far as exercise.
I don't think I need to go through any of the ones that I've already looked at, but if anybody wants to try a fresh one altogether, that'd be all right with me.
Yeah, I don't know. Maybe you should look at like the ones about actually calculating the derivative. These in simple cases.
Yeah, I mean, pick your favorite. The early ones are the ones that I have already looked at.
Yeah. What are the ones you didn't do?
Anything after 3.4 I haven't done yet.
Maybe as a warm-up we'll get the 3.3. So 3.3 is about a simple map from derivable functions defined as just the derivative of x at point 1 squares. And the question, okay, is this a differentiable function? They actually compute the derivative. Sort of as they say in the book, you'll have to redo. Unlike when you learn derivative, where you have all these rules that you can apply, here we sort of have to stumble a bit. You have to, like, they usually say, okay, just try to express f of x minus f of x0 and try to make it look linear, and then try to prove that it converges, and there you have your derivative. But yeah, in this case, you might reasonably expect that have to, because you have squared, you have at x. Then if you think about more, okay, taking the derivative is linear map, so it expresses itself. Have some. I don't know how exactly see it for this. I've done all the exercise myself, and I haven't hooked up my tablet yet, so I can't really solve them practically. Maybe our paper, I don't know. Please talk.
Yeah, so the approach that you mentioned, writing down f of x minus f of x0 and expanding that out, that got me to basically, that's most of the problem, I would say. Writing
Yeah,
that out and then identifying which part of that expression is actually the derivative you're looking for.
yeah. I mean, sometimes the hardest part for me was actually moving the convergence, because I've had this term on the bottom. Can be tricky. I got stuck with that for the graph, but
Yeah, I don't think I went through the exercise of trying to prove that that expression is linear and continuous. It seemed obvious enough that it was.
yeah, it's more about the fact that it can. Let me 3.3. Yes, I can. Yeah, so you have to sort of wrangle some algebra questions out. Uh, oh, the first time I've seen I had so many people on one rest. Fortunately, not that all of the people are speaking, but
If I put tech in spoiler blocks, does it get spoilered?
uh, I don't see any message in the. Why are you typing right now? I don't know. Maybe your original method will be spoiled, but then tech will still interpret it.
That's my guess. I'll try it if there's no objections.
Yeah, right.
All right. Speaking or forever hold your peace.
Yeah. This is one of the simpler
Yeah,
ones. So if
work.
you a reminder that the norm of x here means
Compiler.
the norm of x plus derivative of. Do some algebra for
Compiler.
these
I
expressions.
put compiler, but it showed everything anyway.
Yeah, that's what I expected. End up with some x0. depends on what the people ask.
One thing I was thinking about was in some cases there's functions that have linear constraints. For example, like having the integral on the entire domain, like say it's a function from R to R, something like that. They have a constraint that is linear and whatnot. The derivative there, how do we keep in mind a
You
constraint?
mean what's the derivative of a linear map? Or
Well, if it's a linear map, I will guess the derivative is itself.
yeah, that's the nice thing about linear maps, that they're their own derivatives. So automatically, when you take the derivative of a derivative, there's itself, and someone I'll check that out later. But yeah, so or when you take the derivative operator or an integral operator, because it's linear, unless you're doing it's automatically its own derivative. Nice, because you can try and use that in path length.
If like the function space I'm taking a derivative of as a constraint, like usually, like for example, when we have like in the finite case, you have the functions that can be defined over a manifold, for example, like over the circle, the unit circle, and then you want a derivative in terms of that. Like in the if there's something similar in infinite dimensions, or
I think you can only use the directional derivative in that case, because that's just discontinuous if you have a constraint.
Yeah, it gets messy. I think usually you might get something out of what I did with shortest path, of just sort of having the straight line and then a perturbation, and the perturbations from vector space. If you can like bring back your problem to something of a vector space, I think it gets a lot easier.
So if I constrain maybe the vector space itself, then I can.
I mean, you can just like take a smaller vector space. That can work. As long as you have a vector space, it works. I think I know people, when they try to, they like look at the stability of a PDE, for example. Usually, you say you have a solution, you want to prove it's stable. Usually can't really do that in every direction. Like over the base space, you have to say, okay, let's take a smaller space, that like the space of reasonable perturbations, my real system, and okay, in that case you should linearly stable. Yeah, because it's like general function space, shorted word, bit of the Wild West.
Okay.
I don't quite know the answer to your question, or even if I understood it.
No, it gave me some ideas, so I will maybe even try to frame it better, like if I get more insight.
Yeah, is anyone actually trying to solve this or should I move? Let's actually look at 3.4, because it's actually that chain rule still works. They have ask you first prove that you have f from x to r being differentiable, and at some gamma of t0, then the composition, so f, take t, apply gamma to get into x, and then apply f to that. So this is a function from r to r. You have the differentiable, and the normal function from r to r is the classical derivative in a sense. And the idea is to still show that the derivative of that is just the usual as you. And this exercise is a very simple case, but it actually works in the general case, that the composition of functions still follows the chain rule.
And another thing I was thinking about was if I like differentiability. if it's defined in a dense set, can I say it's differentiable everywhere?
Ooh, yeah, you're asking the very pointy questions here. I'm not sure off the top of my head, but I know that it's also complicated because depending on the author you're reading about derivative, like differentiability and does not always mean the same thing. So already you have some confusion about the definitions. I think if you say this on a dense set, then I guess you can find some results about that, but I have no idea. Works in general.
At the very least, you get that it's continuous in the places where it's not differentiable.
Yeah, I guess you do get that. Well, actually, that's
And regarding like an inverse like an inverse function theorem for derivatives.
oh boy. Yeah, that's I think that's a tricky one because it's even worse than like integrating and getting a constant. Going to move from a function from a linear map, like from a function that takes an x and gives you a linear map from x to y, and recovering the functions have like even more
Because
degrees of freedom.
I would expect that because in multiple dimensions there's a implicit function theorem, and with that you can prove the inverse function theorem. I would expect this hold also in infinite dimension or something similar.
Yeah, that's interesting. I have no idea, and I'm not even sure what to look for because sources on functional derivative be hard to find. You don't find a lot. Yeah, maybe someone has figured that all out. I don't know. But
And
anyway, let's
like
look.
also similarly, like if because for example, like in for function in R, there's like differentiability and so on. But for example, if we look at complex functions, you already get like results of complex analysis with analytic functions and whatnot.
Yes, I
That
did see some. If you look at like the Wikipedia page for Ghetto and Fisher derivative, there are some mentions of okay, when you return the complex, it's a bit nicer. I think it's that in the if you have like some complex Banach space and you look at the Ghetto derivative, it's sufficient to have your Ghetto derivative being linear and continuous for the Frechet derivative, not general.
mm,
But even then, the actual distinction between Frechet and Ghetto can still be messy. I have a colleague who does that sort of stuff, and I talked with him about it. I'm not certain his definition of Frechet and Ghetto derivative are the same one as mine.
so you mean the Wikipedia page of Frechet, for example, or Gateau?
Yeah, I think it's in the Ghetto derivative that they mention stuff about the complex space. Yeah, yeah. Sorry, Shepard,
Mhm.
or you didn't do some of. If you're just jumping in right now, that might be a bit hard. Uh, yeah. I guess I'll just like explain my solution for the four. Take two distinct points on X, and you have a straight line. As I should recap. And okay, we have suppose that some function f is differentiable at gamma of t0, and you have to show that then f of f composed with gamma is differentiable by just t0 and t in R, and just went through the step of f gamma with t minus f composed gamma at t0, steps, and I think eventually you end up. Yeah, first I sort of manipulation gamma t minus gamma t. And that okay, the norm is just expression. Norm of gamma of t x2 times absolute value of t. Then if you that was starting from there being the normal derivative, have some simplification make inject this gamma of t0 minus gamma of t, have this constant factor there, bring me back to the expression with the gamma of t minus gamma of t bottom. So that's just the derivative of f. So this part you have the derivative of f that you can apply, and then it's just a matter of finding the right, because you're trying to find this energy, you would say, okay, for some epsilon, I want to find some delta such that t minus t is smaller than delta, so that this whole expression will stop epsilon. So that, okay, in this case, okay, I need to show we need only some gamma such that this holds to find the result. Guess I didn't. I guess I forgot the. Oh no, okay. This just applies from. Alright, my notes are a bit not super readable. Yeah, the second part is that if you have some function from x to r, which is differentiable and derivative is 0, so mind that this is not 0 the scalar, it's the function that takes point x and 0. Then g is constant, i.e. function whose derivative is 0 everywhere is. Get that again from taking the straight line between 2 points, and finding f is just g applied at my curve, fungible, and f here is from r to r, which and continuous, so that's a constant function, and in particular that g at x1 is just f at 0 is equal to f1 because it's constant. That's equal to g at x2. That here we had taken the x1 and that they are equal because they are arbitrary. Shows that x is a constant. Any questions or other points? And yeah, I don't think it's I'm not the point of going through other exercises right now because I'm not super good at giving them, I don't think, and a lot of people here have been joining in recently. They maybe don't have all the exercises.
So next up is Euler-Lagrange equation. Then.
Yes. Yeah, the
Third-year
next
physics
section is actually
platform.
about the Euler-Lagrange equations, which is another interesting pick because it's not usually part of a functional analysis course. It's all of this something you get in a mechanics course. So start with like Newtonian mechanics with F equals ma. You can only get so far, and then so like Lagrangian mechanics is a step above that to get some solutions for your systems, and it actually relies on the dysfunctional derivative stuff. But usually it's not taught that way. Just formally, it's actually rare not only to have functional derivatives in the functional analysis course, it's actually rare to have Lagrangian mechanics with this function analysis point of view. So anyway, the Lagrangian mechanics is really interesting and really insightful as far as the mechanics go. So definitely worth doing. Yeah, I highly recommend section on Lagrange mechanics. Not that long either. And then I guess the last question is how much time would people like to do that? I'm guessing we're going to have weeks again, but that's up to people. 2 weeks sound good?
I think that's reasonable. There are actually quite a few exercises in here. Some of them are long.
Yeah, I had a quick look. It does seem like. But just to maybe for people who haven't quite the baggage, the idea of the Lagrange equation is that you have this like minimizing optimization problems that we saw here. Okay, you can try and do it. Okay, show that the function is convex and find a stationary point. It's actually a lot of work. And the Euler-Lagrange equations are a way to show, okay, you have this optimization problem, and you just turn it to an ODE, and usually the ODE is easier to solve, so that you get a recipe for solving these optimization problems. Actually, the examples I gave of both the shortest path and both the optimal control theory, one of the ways to solve them is of actually solving the Euler-Lagrange equations. Yeah, I think I don't have much else to say for today or coming.
Thank you for explaining.
All right, have a good one, folks. Thanks for setting this up.
Okay then. See you next time. Bye bye.